All right, greetings, class. Welcome back. Today we are going to talk about kinetic molecular theory in reference to gas particles. Now, you probably need your notebook out to jot down some quick little concepts as we toggle back and forth between this interactive that I have available for you in Canvas. Now, in reference to KMT, KMT stands for kinetic molecular theory. And let's go to our simulation here really quick. All right, so gas particles, they're very, very tiny. We're going to treat them like hard little spheres. And remember, this is an imaginary molecule. In order for us to, for all of our formulas to work, they're going to have zero individual volume. However, they will fill the container, the volume of the container. They're going to have no attractive forces. If they bounce off of each other, they're just going to ricochet. There's no repulsive forces. So think of a repulsive force like something like when you have a magnet and there's a positive and you put them together, they repel. Okay, so we're not going to have any of that. Motion is rapid, random, and constant. When they do bump into each other, the type of collision that they have is called complete elastic collisions. Similar to when billiard balls bump into each other, they're not going to, there's no Velcro, they're not going to stick. So what that means is there's no kinetic energy lost. Okay, so let's go back to our notes. You may have to pause the video briefly as you jot some of the stuff down. So again, very tiny hard spheres, zero individual volume. Oops, sorry. And then we're going to fill the entire volume of the container. No attractive forces nor repulsive forces, i.e. no bonding, no covalent bonding, no intermolecular forces, nothing. Now the motion is rapid, random, and constant, and then again, no kinetic energy lost. All right, so pause your video, jot down some notes, and then we're going to go on to the next thing when you press play. Now, what is temperature? Let's go back to, there we go. Now, temperature is proportional to the average kinetic energy of our molecules. So if I have a lot of kinetic energy, my molecules are really vibrating, they're really moving. And what that is, it's not exact, but it is proportional to the average. So not everybody's moving at the same speed, but the average of everybody is going to be proportional to our temperature, which is indicated by our thermometer over to the right. Now, if I remove some heat, what that really means is that the particles, the average, their kinetic energy is not as great or decreased. Similar, if I have a low temperature, the kinetic energy therefore is proportional and it is even lower. So let's go back to our notes. What is temperature? It's the average kinetic energy in Kelvin, not Celsius. So we have 0 degrees Celsius equals 273. This is our ratio. Going back to our Stoic problems regarding liters, nope, scratch that. Completely forget that. Never mind. We're going to talk about that in the next one. Average kinetic energy in kelvins is proportional. So 0 degrees Celsius equals 273 Kelvin. So what happens at 0 Kelvin? We're going to call this the absolute zero. Now, we can get below 0 on the Celsius side, but we cannot get below 0 on the Kelvin side. So this is when all particles stop moving or vibrating. This is the true zero, Okay, Kelvin measures kinetic energy. So let's go on to our next slide here. All right. Now, when we do some of these example problems, let me erase this really quick. Let me get, there we go. Okay. So let me erase these. All right. For everybody, and let's go back to my little pencil here. All right. So when we're interconverting between Celsius and Kelvin, we have to keep this in mind. This is my go-to ratio. 0 degrees Celsius equals 273 Kelvin. This is my ratio. So what happens if I give you a number and I'm asking you to convert between Celsius and Kelvin, and you're not at 0, but rather you are at 20. So think about it for a second. Did my temperature go up or down? It went up. How much did it go up by? It went up by 20. So therefore, I have to go up by 20 on the right-hand side. They are proportional to each other, 1-to-1 ratio. So I have 20 on the left. I've increased, so therefore I've gone 20 on the right, and we're going to go 293 is our answer. Okay? 273 plus 20. Now, what happens if I'm asking you to go from Kelvin to Celsius? And we have 253 degrees Kelvin. So therefore, we are going to go down. We've decreased. Okay, we've decreased by how much? We've decreased by 20. So if we decrease by 20 on one side, we've decreased by 20 on the other side. So now we have a negative 20. Oops, let me fill that in. Now, what happens if I say, well, Kelvin went all the way down from starting at 273, and now it's at 0 degrees Kelvin. What is that in Celsius? Well, how much did we go down by? We subtracted, or we've gone down 273. So if you've gone down 273 on the right, you will go down 273 on the left. So now we're going to have a negative 273 degrees Celsius. So here's some just quick examples on how to interconvert between Celsius and Kelvin. They are a 1-to-1 ratio, and the reason why we use Celsius often in chemistry is because of the fact that there is some proportionality between Celsius and Kelvin. All right. Now, let's go back to our let's go back to our temperature scales here. Again, this is just a little diagram to help you see that we have a 1-to-1 ratio between Kelvin and Celsius. I start at 273. Let's go to 283. We've increased 10, therefore we've increased 10 on the Celsius side. However, we don't use Fahrenheit at all in this course because of the fact that it's not a 1-to-1 ratio. For example, let's go all the way back down. 273 Kelvin is 32 degrees Fahrenheit. So let's see if we go up 10 on Kelvin. We go up. We increase by 10 for Celsius, but look what happens for Fahrenheit. We've increased not 10, but we've increased from 32 to 50, which is obviously a lot greater than 10. So these do not, there is not a proportionality constant of a 1-to-1 ratio with Fahrenheit, therefore we don't use it. All right. So quick recap. 0 degrees Celsius equals 273 degrees Kelvin. If you increase one side, you got to increase the other side. If you decrease one side, you got to decrease on the other. Okay, absolute zero is when all particles stop moving. That is when we are at the true zero, so that's 0 Kelvin. And then remember that we have elastic collisions. There's no kinetic energy lost, and we're going to treat these gas particles like little, very tiny hard spheres with, and treat them just like perfect little gas particles. And we're going to call these gas particles ideal. I hope this has helped, and we're going to move on to the next section shortly.